Okay, so for this first case, we have cos cubed x. We know that for our trig identities, they usually involve cos squared, right? Like sine squared plus cos squared, and so on. Okay, or cos squared minus sine squared, those ones. Okay, so here we've got cos cubed. We would like to work with cos squared, because that fits in more with the identities that we know. So we can separate this out into a cos squared part and a cos part, just to make things a bit easier. So here, this is equal to the integral cos squared x times cos x dx. Okay, I'm going to underline this bit here. So this gives us a hint at what the u substitution will be. We've got cos x dx. If we let u be sine x, right, then that cos x dx, that's just going to be du in that case. Okay, so that gives us a hint as to what to do. Okay, since we've got cos x alone, we let u be sine. But if we look at the rest of the integral, we don't have sine. We've got cos squared. But with a trig identity, we can change cos squared into something with sine. Okay, so that we can do the u substitution. Now we know that sine squared plus cos squared is 1, so cos squared is 1 minus sine squared. So we can fit that in. So here, this is the integral. Okay, 1 minus sine squared cos x dx. Now this looks like what we want for the u substitution. If we let u be sine x, then du will be cos x dx. That takes care of that. Okay, so here it just goes to a normal u substitution. So u is equal to sine x. Du is therefore cos x dx. That handles that bit at the end that we factored out. Okay, so let's just substitute. So this is going to be the integral 1 minus u squared, and then everything else that takes the form of du, right? That cancels everything there. So now this is just an integral in terms of u. That's very easy to do. So this is going to be u minus 1/3 u cubed, and then remember the plus c, because this is indefinite. Okay, now we're not done. We've got the u, but we want to put the x terms back. So remember, u was sine x. So this is going to be sine x minus 1/3 sine cubed x plus c. Okay, quite straightforward. So in this case, if we have something with cos, and it's like an odd power, like here we've got cos cubed, if we take out a factor of cos, we're left with cos to an even power. And if it's an even power, we can use those identities with cos squared. Okay, it makes it a bit easier to get sine, in this case here. And then everything we factored out, that ends up being du, so that goes away. Okay. Okay, let's have a look at the next example. Okay, so this is sine to the 5x cos squared x dx. Okay, now again, we quickly look at this and see what we can do. Here we've got an odd power of sine, and then an even power of cos. Notice that if we factor out sine, then we get sine to the 4. That's even. We can use one of those trig identities. Okay, if you don't have sine squared, in this case we'll have sine to the 4, that's just sine squared squared. So we can still use those identities. It's just squared. And then cos squared, that's easy. We can change to whatever we need. Okay, but the emphasis there is on the sine to the 5. Since it's odd, we can take out a sine, factor it out, and then we're left with even powers, and we can work with that. So here, since it's odd, we can take out a sine and see what's left over. So this is the integral sine to the 4 now, cos squared x, sine x dx. And again, I'm just going to underline that. We want that bit to go away with our u substitution. Okay, so if that bit we want to go away, we should let u be cos. Because if u is cos, then du is minus sine x dx, and that takes care of that underlined bit. That will go away. Okay, so remember, u must therefore be cos, right? So that the du takes care of the sine. We've got sine to the 4 and cos squared. For cos squared, that's fine. It's already a cos. Sine to the 4 is not a cos. We need to change it to something with cos. Okay, but it's sine to the 4, it looks a bit difficult. Let's write it as sine squared squared. It makes it a bit easier to work with. So this is going to be the integral sine squared x squared cos squared x sine x dx, and I'm still going to leave that out there. The du is going to take care of that in a bit. Okay, now we said we want u to be cos. We've got sine squared. We need to change that to cos. Remember, sine squared plus cos squared is 1. We can change that. So this is going to be the integral 1 minus cos squared. Okay, but that takes care of the sine squared. It's still squared. Okay, so we need to put the squared still. Okay, cos squared x, and again the sine x dx over there. Okay, so this is what we want it to look like now. The first bit, those are all in terms of cos. If we let u be cos, du will be minus sine x dx. That takes care of the second bit there. So we just do a u substitution. So if u is cos, du will be minus sine x dx. We just need to take care of the minus sign, but that's not a big problem. So minus du is sine x dx. Okay, we can just put the minus right in front. We don't need to worry about that. Okay, so all the causes, that's going to change to u. The sine dx, that will be du. And then the minus in front. So that will be 1 minus u squared squared, u squared du. Okay, now this is something we saw last semester, so nothing new with that. We can just multiply everything out, and then it's just a polynomial. Okay, so nothing new with that. Okay, so this will be 1 minus 2u squared plus u to the 4, another u squared there. Okay, again, we can just take the u squared inside. So we end up with u squared minus 2u to the 4 plus u to the 6 du. Okay, straightforward power rule. Add 1 to the exponent, divide. We've done that many times now. So that's minus u squared. That will be 1/3 u cubed. This will be minus 2/5 u to the 5. 1 over 7 u to the 7 plus c. Okay, now we're not done. This u, we put the u there. We want it in terms of x. Okay. For the quiz, a lot of you just left it in terms of u. If you did a u substitution, the question's not finished with that. You need to put the x terms back. Okay, so if you look at your scripts, when you collect them, you'll see I put a little marker there. It means your answer's not finished. Okay, there's a step missing. Okay, so we can put the, what did we let u be? We let u be cos. So wherever we see a u, we just put a cos now. Okay, so this will be minus 1/3 cos cubed x plus 2/5 cos to the 5x minus 1/7 cos to the 7x plus c. Okay, so not much thinking required. Just wherever you see a u, you then put cos back there. Okay, please remember the last step. Your answer is not in terms of u. You came up with that. It must be in terms of x. Okay, so please, when you're answering these questions, make sure you put that last line in for your final answer. Okay, so a quick summary of what we did for this. So we saw sine has an odd power, cos had an even power. If we took out a factor of sine, it now becomes an even power. If it's an even power, we can use our trig identities. Right, sine squared, cos squared, those are all even powers. Okay, so we took out a sine. We changed everything else to a cos using our trig identities. If everything else is a cos, we can let that be u, and then du takes care of the sine. Okay, and then once that's done, we've seen that last semester. That's nothing new with that. Okay, so again, if you have an odd power of sine or cos, take one of those terms out. You're then left with even powers, and then with even powers, you can use those trig identities to convert to whatever you like. If you have even powers of cos, you can convert to sine. even powers of sine, you can convert to cos. You can go whichever way you need. Okay. Let's have a look at this one. So here we have the integral sine squared x dx. Okay, so this is different to what we had before. The previous two examples had an odd power for cos and an odd power for sine. Here we don't have any cos, and the sine is just an even power. So we can't use that trick that we had before. But we can use another trig identity, right? That half angle, double angle, those identities. Sine squared we can write in terms of cos, right? But not cos squared, that's just going to change the problem. We can write it like this. So this is going to be the integral 1/2, 1 minus cos 2x. Okay. Remember your half angle, double angle, so on. If we have sine squared, we can write it in terms of cos like this. If we wrote that as 1 minus cos squared, well then we just have a cos squared to worry about. That doesn't help. So here, if it's just sine squared by itself, we can use the identity there. And this is easy to do. We know how to evaluate these now. Okay, so this is going to be the integral 1/2 minus 1/2 cos 2x. Okay, so this is just going to be 1/2 x plus 1/4 sine 2x plus c. Okay, so nothing new with that. Once we've applied our trig identity, we've seen that before already. There's nothing new with that. Okay, so it's just integrating cos. That's just going to become sine. That stays just sine. Okay, yeah, so just remember your minus signs here. If it's sine squared, if you're using this identity, it comes with the minus. If we're doing it with cos squared, we'll see in the next example, it's a very similar identity, but with a plus. Okay, so just remember what goes where with that. Okay, so this was sine squared. We can do the same thing with cos squared. Okay, again, very similar to the previous one. We don't have any odd or even powers of sine. It's just cos squared. Now, if it's just cos squared, if we change it to sine squared, again, it doesn't help us. You're just rewriting the problem to something like we did here. Okay, so instead of converting it, we're going to use that, the double angle, half angle formula, so on. Okay, so cos squared, we can write it similar to the previous one. That's going to be 1/2, 1 plus cos 2x. Okay. If you are confused with these identities, just remember the double angle with the cos. Remember, cos 2x, that's cos squared minus sine squared. If you remember that one, you can easily get to this one here. Okay. This becomes the integral 1/2 plus 1/2 cos 2x. Okay, very similar to what we had before. So the integral 1/2, that's just half x. Okay, integral of cos, that's just sine. So that's 1/4 sine 2x plus c. Okay, so you don't need to worry about the sine 2x. There is an identity for that, right? The 2 sine x cos x. Once you've written it like this, that's fine. Please don't do any more simplification. Okay, any questions so far? Okay, let's have a look at the next one. So here we have the integral sine to the 4x dx. Okay, so similar to the previous one, where it was just sine by itself with some even power, here again we have sine to some even power, in this case 4. So now we want to figure out what to do. Again, it's not so easy to factor anything out, because if we take out a sine, we're left with sine cubed. That doesn't help us. There's no identity with sine cubed. So instead, we're going to do something similar to what we did before. but now we're going to write it as sine squared squared, and then we're going to do the same thing as before. Okay, right, because it's a power of 4. So this is going to be the integral sine squared x squared again dx. Okay. Now, don't worry so much about the outer squared, we'll get to that. The inner part, sine squared, we can use the same identity as before. Okay? So this is going to be equal to the integral 1/2 1 minus cos 2x. Right? The minus goes with the sine, the plus goes with the cos. Okay, and then all of this is then squared. Okay, so I've just replaced the inside part with the identity that we already used before. Okay, so let's square this out, see what we get. So the half squared, that would be a quarter, we can take that out. Then we're left with 1 minus 2 cos 2x plus cos squared 2x. Okay, so getting better. The 1, that's easy. Cos 2x, that's easy. Cos squared 2x, that's pretty much the problem that we had before. So again, if we have cos squared of something, just because it's a 2x doesn't mean it's totally different. We can change this again into something with cos. Okay, so let's do that. So this is going to be 1/4 integral 1 minus 2 cos 2x plus 1/2 1 plus cos 4x this time. Okay, why 4x? Because the identity is twice whatever we had originally. So if it's cos squared x, we get cos 2x. If it's cos squared 2x, we need to double the angle again, so it will be cos 4x that time. Okay, so this will be 1/4 integral. We've got a 1 plus a half there, so that will be 3/2 minus 2 cos 2x, and then plus a half cos 4x. Okay, and we've done all of that before, right? Integral of cos and sine, easy stuff. So this will be 1/4, 3/2x. Integral of cos, that will be sine, but we've got that extra 2 there, so it will be minus sine 2x plus 1/8 sine 4x plus c. Okay, you can multiply the 4 inside, but the quarter inside, but that's not necessary, right? We can stop there. Okay, but if you want to multiply everything out, that's fine. Okay, and again, you got the sine 2x, we could use an identity for that. Sine 4x, we could use an identity for that, but this is fine as is. Okay, you don't need to simplify anymore. Okay, if you need this answer for another question, okay, maybe it would be nice to simplify, but here, if it's just this, then you can leave it as is. Okay, any questions about this one? Okay, so pretty much exactly what we did in the previous case, except here we did this identity twice, right? Because we got the sine squared, we changed it over there, and then the cos squared we had to change as well. Okay, so we just did that twice. Okay, any questions? Okay, so it's just using trig identities. Once you put all your identities in, it's just the normal trig integrals like we've done before. Okay, so these are ones with sine and cosine. We know those identities. The next few will be tan and sec. Okay, those other trig identities. Okay, so we have the integral tan to the 6x sec to the 4x dx. Okay, so instead of using those sine and cosine identities, now we can use the sec and tan identities. Okay, now what do we know about the sec and tan functions? Okay, well, the derivative of tan is sec squared, right? That's one thing we know. So if we take out a tan, if we take out a tan, we're left with tan to the 5. That doesn't help us, right? Because those identities are with tan squared. Tan to the 5, that's not going to help. Okay, what about the sec? If we take out a sec squared, we've got one sec squared left over and another sec squared left over. And remember what I said with that derivative? The derivative of tan is sec squared. So we've got a tan there, and then the sec squared that we left there, we can convert to tan, and then we have a sec squared left out. So it's very similar to what we did in the first example with the cos and the sine. We factored something out that would be with the du, and everything else we changed to something we could let u be. We can do the same thing here. So we can take out a sec squared. So this is the integral tan to the 6x sec squared x sec squared x dx. Okay, so why the sec squared? Well, we can't do anything with the tan. If we take out a tan, tan to the 5 doesn't help us. So the next best thing is to take out sec squared. Okay, so now remember the derivative of tan, that was sec squared. So we want u to be tan. So everything in that first bit we want to be tan, so that the derivative is that second bit over there. So tan to the 6, that's fine, it's already tan. Sec squared, we need to then change to tan, and then we're fine. Okay, so which identity do we use? 1 plus tan squared is sec squared, so we can make that replacement. So here, this is the integral tan to the 6 sec squared. We want to change to tan, so we can do that easily with 1 plus tan squared. And then we still have the sec squared x dx left over. Okay, now we can do our u substitution. We have everything that we need. All of those tans in the first bit, okay, tan is u, that's fine. Then the derivative is sec squared, so that second bit over there, that will then be du. That cancels all of that out. So u is tan, du is sec squared. Okay, so that cancels the sec squared that we wanted to get rid of. Okay, so now we can just do the replacement. So u is tan, and then du is that bit over there. Okay, so this becomes the integral u to the 6. Okay, that comes from the tan to the 6, and 1 plus tan squared, that will be 1 plus u squared. Okay, and then back here, sec squared, that was the du, so we can just put du. Okay, and this is much easier to work with. Okay, no trig functions at all, just polynomials in u. So this is the integral u to the 6 plus u to the 8. So that will be 1 over 7 u to the 7 plus 1 over 9 u to the 9 plus c. Okay, remember what we did? We let u be tan. So we need to put the tan back here. So this will be 1 over 7 tan to the 7, 1 over 9 tan to the 9. And then the plus c. Okay, so very, very similar to what we did with the sine and the cos. Remember, derivative of sine gave us the cos that we needed. The derivative of the cos gave us the minus sine that we needed. Very similar, it's just that the roles are swapped now with tan and sec. The derivative of tan now gave us the sec squared that we needed. Okay, so it always goes back and forth like that. Okay, now for the next example, we'll go the other way around. If we let u be sec, then that will give us the sec tan that we need. Okay, very similar to the sine and the cos. Okay, so this is the integral tan to the 5, sec to the 7. Okay, very similar to the previous one, but what makes this different? In the previous one, we had those even powers. So we had even powers of sec, which means we could take out the sec squared. Okay? Here we've got odd powers. If we take out a sec squared, that doesn't help us. Okay, right? We're left with sec to the 5. That's no good. So here we can't do that. We can't take out sec squared. So we use the other term that we know. Right? So before, The derivative of tan gave us the sec squared that we could take out. Now we're going to take out a tan. We're going to take out a sec, and then the leftover will be, what's the derivative? Derivative of sec is sec tan. So we have to take out a sec tan in this case. If we take out a sec tan, we're left with even powers. Even powers are good because we can use our identities. Okay, so if it's odd powers, we take out a sec tan. Why? Because we're left with even powers, and with even powers, we can use the identities. Okay, so that's what you should be thinking, just quickly looking at the question. If they're even powers, we can take out a sec squared and do what we did before. If it's odd powers, we can take out sec tan, and then we're left with even powers. Okay, so in the end, even powers are good for those identities. Okay, so this will be tan to the 4, sec to the 6x, sec x, tan x. Okay, again, underline that. We want to get rid of that bit with our du. Okay, so u should be sec, and then the du will be the sec tan. That other part will go away. Okay, so if we want u to be sec, the sec to the 6, that's taken care of. It's already sec, no problem there. The tan, that's a problem. We need to convert that into sec. Okay, now we know tan squared and sec squared, we can convert between the two. This is tan to the 4. So we're going to write it as tan squared, squared. Okay, so tan squared on the inside, and then whatever we do to that, we square it. The sec, that stays the same. And then the leftover part, we want that to be our du in the end. Okay, again, always keep in mind, we're trying to get this first bit to sec only. Okay, so whatever you do to the first bit, whatever identities you have, work your way towards something with sec. So we had tan to the 4, we write it as tan squared, squared, and now the tan squared we can write as something with sec. Okay, that will be sec squared minus 1. So that will be sec squared minus 1 for the tan squared, but again, everything's squared there, so squared. Okay, again, let me just underline that. That bit's going to be taken up by the du. Okay, so the first bit, we've got the sec squared, we've got the sec to the 6. Okay, no tans involved anymore. We can do our u substitution. So if we let u be sec, that will be the u squared, u to the 6, that's taken care of. Du will be sec x tan x, that's taken care of as well. Okay, so here, u is equal to sec x for the whole first bit there. Then du, that will be sec x tan x dx. Okay, that takes care of all the underlined parts. Okay, so let's do the substitution now. Okay, so wherever we see a sec, we now put u. So this will be u squared minus 1 squared. U to the 6, that will be the sec squared. And then everything else is the du like we wanted. Okay, so we've got a bit of expanding to do, but at this point, there's nothing new. We've done polynomials many times already. Okay, so let's just expand it out. So this will be u to the 4 minus 2u squared plus 1, u to the 6. Okay, similar to what we did before, and then we put the u to the 6 inside. So that will be u to the 10 minus 2u to the 8 plus u to the 6. Okay, standard exponents now. So 1 over 11 u to the 11 minus 2 over 9 u to the 9 and 1 over 7 u to the 7. Okay, and the plus c. Okay, so again, a number of you are not putting in the plus c. Please remember, indefinite integral always comes with the plus c at the end. Okay, and on the other hand, a lot of you are putting plus c for the definite integral. Okay, that's wrong. If it's a definite integral, your answer is a number. You don't go and put plus c onto a number. Okay, so please remember, indefinite integral comes with the plus c, definite integral, no plus c. Okay, what did we let be u? If we go back up here, u was sec. Okay, so wherever we have a u, we put the sec back. So that's 1 over 11, sec to the 11, minus 2 over 9, sec to the 9, plus 1 over 7, sec to the 7. And again, the plus c. Okay, so very similar to what we did before with the sine and the cosine. It's just now we're working with sec and tan. But the idea is still the same. You factor out the part that you want to be the du at the end. Everything else you change so that you can substitute u. Okay, any questions on this one? Okay, and again, a nice hint here. Odd powers, we can take out a sec tan. If it's even powers, we can take out a sec squared. Okay, so that's a little hint as to what to do given a particular integral like that. Okay, next one, integral tan cubed. Okay, so here, a little bit different. Okay, like we had with the sine cubed and the cos cubed and so on, if it's just this by itself, there's no factoring we can do, right? We can't take out a tan, because the leftover will be tan squared. You can't do much with that. Okay, because remember, the derivative of tan was sec squared. Okay, so that doesn't help us so much. So what we can do instead is factor it. Tan x times tan squared. Okay, but there's no u substitution we can do. We kind of just need to work with the trig identities. Right, there's no sec, so that doesn't, we can't do what we had before. So instead, we're just going to work with some trig identities to get to something that we can integrate. Tan cubed, no, but maybe we can change it to something that we can. Okay. Tan by itself, not much we can do with that. The tan squared, we can change to something with sec squared. So let's do that. So that's tan x. This will be sec squared x minus 1. Okay, it doesn't look like we've done much. It looks a bit more complicated than what we had before. But we'll see that when we multiply this out, the resulting terms we can integrate directly. So before, can't do much, we use our identities, and we'll see we can do this in one line afterwards. So here we have tan x, sec squared x. Okay, I'm just going to underline that for the emphasis there. Dx. Okay, I'll write it as two parts so we can see them separately. And then minus integral tan. Okay, now I underlined the sec squared there because if we let u be tan, then du is sec squared. So we can do that in one line, right? Because that will just be u du. That's very easy to do. On the other hand, the tan, we've done that one before with the u substitution. So you can do it in one line or you can do it the longer way. If you want to do it the longer way, remember that this is the integral of sine x over cos x dx. If we let u be cos, then du will be minus sine x dx. So that takes care of the top part. So we can write this as minus the integral 1 over u du. Okay, so that's just minus the log of cos. Okay, so that's just the u substitution. If you've done it before, you don't need to rewrite it. If you know the integral of tan off by heart, you can just write the answer. Okay, you don't need to do extra working. Same thing with the integral of the natural log. Okay, you don't need to do all that working again. You can just put the answer down. Okay, but if you want to put the extra working, that's fine. Okay, so this one, we said u was tan, du is the sec squared, so this just becomes 1/2 tan squared x. Okay, and then this other one, this was the minus natural log of cos. Okay, so you can write it like that, or you might see it written in terms of sec. Right, because 1/cos is sec, so you can write it both ways. Okay, in the textbook it's written like this, but if you do want to write it in terms of cos, that's fine as well. Plus c. Okay, so this one didn't follow the same rules as before, okay, because it's just tan by itself. There's no factoring we can do, so that doesn't help. Okay, but we can use our trig identities to rewrite it into something we can integrate. Okay, so sometimes you can do the factoring with the u substitution, other times you just use your trig identities to get something that we know already. Okay. Other times you can do both, right? You can do trig identities to change it and then do trig integral. Okay, like this, you'll get the same answer in both cases. Yep. The second to last step. So for this first integral, I'll let u be tan. So if u is tan, then the derivative du just becomes sec squared. So we integrate u, that's 1/2 u squared. Since u was tan, it's 1/2 tan squared. Okay, and then for the other part, that was another u substitution. So we rewrite tan as sine over cos. You let u be cos, so the top part becomes minus du, and then that's just the natural log of cos. Okay, and you can put the minus sign inside to write it as the natural log of sec. Okay, you can go back and forth. I don't mind which one you use. Okay, is that all right? Okay, any other questions on that? Yeah. Yeah. Yeah, that was from this bit. So this would be minus the natural log of u. And then u was cos, so we can put cos inside. Or you can take the minus inside and write the cos as sec, because there will be 1/cos, which is sec. So you can write it as minus the natural log of cos, which is the same thing as the natural log of sec. Why? Because sec is 1/cos. Okay, so that minus sign you can put inside to make it 1/cos. 1/cos is sec. Okay, you can write it either way, I don't mind. Okay, it's just a minus sign difference between the two. So you either put the minus sign inside to write it as sec, or you leave the minus sign on the outside and write it as ln cos. Okay, but if you're writing the minus sign on the outside, remember minus minus makes a plus, so we want to work with as few minus signs as possible. Yeah. Yeah, question there? No. Okay, anyone else with questions? Okay. Okay, so that's the most of the types of problems that you're going to get. So even powers with sine and cos, odd powers with sine and cos, even powers with sec and tan, odd powers with sec and tan. So we've covered all the possibilities here. Okay, the last thing that we need to go through is if we have products of sine and cosine. Okay, so without powers, so just sine cos, cos with cos, sine with sine, those types of things. So here, integrals of the form sine A cos B. Okay, so no powers of sine and cos, just sine and cos like that. Okay, integral sine A sine B, and finally cos A cos B. Okay, so those are all the combinations, right? You can have sine with cos, sine with sine, cos with cos. There's no other combinations there. Okay, so with these types, there's no u substitution that we can do, right? Because we just have sine and cos. A and B, we don't know what they are, so we're kind of stuck with that. If it was sine x cos x, that's a bit easier to work with. Or if it was like cos x cos 2x, maybe you could do a trig identity. But in general, there's not much you can do. Okay. But what we can do is use those trig identities with the sine a plus b, or the sine a minus b. Remember those ones with the sum? Okay, so recall, if we have sine a plus b inside the brackets like that, we can write this as sine a cos b plus sine b cos a. Okay, they swap for that second term. Okay, then if we have sine a minus b, exactly the same, just that plus goes to a minus. So this will become sine a cos b minus sine b cos a. Okay, so like I said, the terms are the same except for that minus sign there. If we add these two together, those terms on the end there will cancel. So let's add these two together here. Okay, so we end up with sine a plus b plus sine a minus b. Okay, the term with the plus and the term with the minus, they're going to go away. So we have sine a cos b plus sine a cos b. Well, that's just two of them. Okay, a little bit of rearranging. You can take the 2 over to the other side. We end up with sine a cos b is sine a plus b, whatever that might be, plus sine a minus b, again, whatever that might be, over 2. So before we had a product of two things, we didn't really know what to do. Sine by itself, we can integrate very easily. And then on the other term there, that sine, we can integrate again quite easily. So we've turned a product into a sum of two sine terms, very easy to integrate. Okay, and we can do the same thing with cos a plus b and cos a minus b. Okay, so let's have a look at that. So cos a plus b, that's going to be cos a cos b minus sine a sine b. Cos a minus b, that's going to be cos a cos b plus sine a sine b. Okay, again, the terms are the same except for that minus sign. So again, if we add them, then those last two will cancel, and we're just left with those first two. Okay, these ones there. Okay, so adding them, we get cos a plus b plus cos a minus b is 2 cos a cos b. Okay, same as before, we can then divide by the 2. So we're left with cos a cos b is cos a plus b plus cos a minus b all over 2. Okay, so if we have a product of cos, then we can use this identity here to write it as a sum of cos terms. And that's much easier to work with. Okay, the last one, I'll leave that for homework. Okay, so find the identity for sine A, sine B. Okay, so like we did for the previous two, follow the same sort of steps, but now do it for sine A, sine B. Okay, so that will be for homework. Okay, so let's do one example with this here. So let's say we have something like this with the sine A and a cos B together, and then we're going to use that identity to simplify. Okay, so we have the integral sine to the 3x cos to the 7x dx. Okay, so here we know what the a and the b should be. So a, that's the 3x, and then the b, we've got the 7x. Okay, now sine 3x, there's no identities with that, right? We've got cos 2x, we know how to work with that. Sine 2x, we know how to work with that. Sine 3x, not much to do. Same thing with the cos 7x. Cos 2x, we can work with that, but cos 7x, that doesn't help us. Okay, so we're going to use this over here. Okay, sine A cos B. Okay, we know what the A and the B are in this case. So that's going to be sine A plus B, so the sum of A plus B, plus, and then same thing with the difference of A and B. Okay, all over 2. So this is going to be 1/2 the integral sine with the sum, plus, okay, so this one comes with the plus there, and then the difference. Okay, so this is going to be 1/2 integral 3 plus the 7, that will be 10. Okay, and then the 3x minus the 7x, what do we get for that? What do we get? 3 minus 7? Minus 4. But remember, if we have sine of a minus something, we can take the minus out, right? Because it's an odd function. So here, we can write this as minus sine 4x. Okay, so that saves us with the problems of the minus sign inside there. Okay, now this is just straightforward. Integral of sine, that's going to be minus cosine, and then we just have those factors that we need to divide by. Okay, so this is going to be 1/2 minus 1 over 10 cos 10x, and then plus 1 over 4 cos 4x. Okay, plus c. Okay, then we can take the half inside. Not really needed, but let's just finish up here. So it's minus 1 over 20 cos to the 10x, and then we've got a plus 1 over 8 cos to the 4x plus c. Okay, now the cos and the cos over there. Okay, we could use identities with the cos 4x. It would be a bit difficult, but we could. But this is fine. Okay, once you've integrated and you simplified, you don't need to do any more identities to simplify that. Again, maybe a follow-up question involves the previous one. Maybe it would be better to simplify if you could, but here there's no real simplification we can do. Okay, any questions on this one? Okay, let me give you some homework for these product ones. Okay, so I'll give you one from each case. Okay, so the first one, let's have the sine and the sine. So we have sine 2x, sine 3x. Okay, for the next one, let's have the sine and the cosine. So let's have sine x, cos 2x. Now with this one, the cos 2x, we could use a trig identity on that. So you could change the cos squared, the cos 2x into cos squared minus sine squared. You could see what happens with that. So I'll put a little star, try that out, see what you can do. But we know that sine A cos B, we can write it with that identity we had before. Okay, but again, you could change the cos 2x into cos squared minus sine squared, and then you'll see that becomes very similar to the third, the first one that we did today with the cos cube. Okay, and then the last one, cos with cos, let's have cos 3x, cos 5x. Okay, so we've got sine with sine, sine with cos, but we could do that a different way, and then cos with cos. Okay, that takes care of the possibilities there. Okay, any questions about about this product over here. Okay, so the sine with the sine, the cos with cos, and sine with cos. Any questions on that? Okay, so a quick little, I don't know, study guide, help guide, something like that. So if we have the integral sine to the kx, cos to the mx dx, what do we do in the different cases? If we have sine to the odd power, we could take out a factor of sine and change the rest to cos. So k odd, take out a sine factor, right? Because if k was odd and we take out a sine factor, we're left with something that's even. And we can work with that. So take out a sine factor, change the rest to cos, like we did for question 2. Okay, and if we change the rest to cos, that's what we have our u, and then du is the sine. Okay, now if m is odd, we can take out a cos, and then change the rest to sine. So if m is odd, we can take out a cos factor. Okay, why? Because if it's odd and we take out a cos, the leftover is even, and we can use our trig identities with that. Okay, if we take out a cos, we want that to be part of our du, so everything else must therefore change to sine. Okay. If both of them are even, then you can use a trig identity with that. It's not so straightforward like these rules here. And if both of them are odd, well, you can take out one of them, or you can take out the other one. You can take out the sine, or you can take out the cos. There's not much more you can do with that. Okay, so that's for sine and cos. Okay, we know what to do for that. What about sec and tan? So let's say we have the integral tan to the kx sec to the mx dx. Okay, now we knew what to do here. If it was even powers, okay, we got even powers, we could take out the sec squared. Why? Because the derivative of tan gave us that sec squared. So both even, factor out the sec squared. Why? Because if we let everything else go to tan, the derivative of tan will be that sec squared that we wanted to get rid of. Okay, change the rest to tan, and then the derivative will be the sec squared. And that's if they're both even. If they're both odd, then we can take out a sec tan. Why sec tan? Well, because the derivative of sec gives us the sec tan. So both odd. Take out sec tan. Okay, we want to get rid of that with the du part. So u must be sec to get rid of that. So change the rest to sec. Okay, and then that tells you what u should be. If everything else is sec, then u is sec. Okay, then if it's something different, if one is even and the other's odd, or if it's just one by itself, like question, the last one we did with that tan cubed, if it's just tan by itself or sec by itself, you're going to have to do some trig identity on that. Okay, it's not so straightforward. So like with the tan cubed, there's no identity with tan cubed, but there is an identity with tan squared. So we take out a tan and apply the identity to tan squared and see what we can get. If it's sec cubed, something similar, right? Sec cubed doesn't have an identity, but sec squared does. So you can take out a sec and then work with the sec squared. Okay, and then finally, if you have something with sine A, sine B, cos A, well, we had sin A cos B, let's write it like that. Sin A cos B, or cos A cos B. We use those identities. There's nothing, there's nothing else that you can do with these ones. Okay, so we had the identity for sin A, sin B, that was for homework, and then there's other two, I gave you those. You just apply the identity, and then you get integrals with sine and cos. And that's everything for trig integrals. Okay, so you just need to know those rules for sine and cos, the rules for sec and tan, and then the rules for these products. So it's just three things. Okay, any questions before we finish up? Okay, no. Okay, so please have a look at the tutorial number 3. I'll have a bunch of these for you to try out. Also, in the additional notes and work section on Learn 2024, there's a little file there, extra homework or something like that. There's some extra problems there as well. Okay, that you can try. But if you can do the tutorial problems, that covers all of these different cases. Okay, any questions? Okay, cool. I'll see you tomorrow.